Welcome back to the Demystify Sci podcast. Today we are sitting down for our second conversation with Dr. André Assis. And last time we explored a long-lost theory of electrodynamics from Weber and friends. And today we are talking about one of the central cosmological issues which concerns an idea from Ernst Mach about the production of inertia and how gravitation ties into inertia, how it is that the widespread structure and distribution of all of the material in the universe plays into what keeps objects in their motion, and what causes strange anomalies that we generally associate with this concept of inertia. You know, a lot of things are associated with inertia. When you're a kid, you're told, well, something stays in motion because of inertia, unless something acts upon it. And you're like, okay, but what's inertia? And so by examining the works of Mach in today's discussion, we hope to actually put, well, I don't know that we'll get to the entire bottom of that, but I think we'll get a lot closer, and we'll actually have a sense of what causes something to stay put if it's already staying put. And what does it stay put with respect to? Is it with respect to absolute space, as Newton believed, or Einstein? Or is it with respect to other bodies in the universe? And so we're going to tear apart those, and Professor Assis has some really cool demonstrations that he's going to do for us in this podcast, and you can actually see the effects for yourself and make up your own mind, which is the best case scenario for science as far as we can tell.
Indeed. And it's tied into a lot of the conversations that we have on the show and other places, because there's these fundamental rifts in some of the theories that are ascribed to Newton and Einstein that have become so ensconced in the nature of modern science that it's almost impossible to question them. But motion forward requires us to actually ask these questions and see if, as heretical as it sounds, if there's a better way of interpreting the data that we have than the stuff that Newton and Einstein came up with. And so we're grateful that Dr. Assis came back and kind of guided us through that entire world.
Yeah, and I think this is going to illuminate some of the discussions we've had with Dr. Unzicker as well. So if you've been following those, we're going to be filling in some of the gaps with those conversations as well. I know Dr. Unzicker is also equally obsessed with Mach's formulations. And so Mach is another one of those shadowy characters that everybody sort of gives a nod to, but his foundational ideas haven't persisted into the celestial mechanics that we uphold today, the popular ones anyways, which is basically relativity and the standard cosmology. But if we take Mach seriously, we might end up with a very different conception of how this place works. And it seems to be a bit less paradoxical than we would have otherwise. So we're interested in that. We get into all of it, get into the cosmology, get into the CMB, all our favorite topics. So I think you guys are going to love this one.
If you enjoy the Demystify Sci podcast, consider supporting us. You can come over to patreon.com/demystifysci, sign up to give us a couple dollars a month, and you allow us to maintain editorial freedom. You allow us to never have sponsors or advertisements where we are reading you things about buying underpants or ties or razors or whatever it is that people are shilling. And you get to join one of the best communities on the internet at our Sunday patron chat, where we get together and we talk about all of the ideas that are beyond the scope of the podcast. It's just the context for all of science.
If you want to hang out in person, please consider coming out to our first live event, which is happening really, really soon in Austin, Texas, on the weekend of April 7th and 8th. We're going to be gathering together to watch the total solar eclipse there, but also enjoy some incredible talks and workshops and really just put our minds together about where these explorations should go next. So I would love to see you there. We have tickets available. There are still a few seats left, and you can grab a link up here in the corner.
And in the meantime, enjoy our conversation with Dr. Assis, and we will see you next time.
The scientific revolution starts now.
The Demystify Sci podcast.
Let us see in the dark.
We've talked about Mach's principle a bit on this show. It's very interesting as a concept because
Should we tell people what it is?
Yeah, exactly. I was going to introduce that, but maybe you can tell people what Mach's principle is. But I wanted to just add that it's interesting because it comes from Mach's mechanics, but Mach never referred to it as his principle or anything, right? It was referred this way much later as people built upon it. So maybe you can outline the story of Mach's principle.
Yes, okay. So maybe we can begin with the simplest experiment of dynamics, because physics, we have statics, which is due to Archimedes, 300 before Christ, the law of the lever, equilibrium, floating bodies, and so on. But dynamics, essentially, it begins with Isaac Newton. And so I have here Newton's apple. So if we don't have statics, so the simplest problem is that of a two-body, like the ears and the apple. And if I neglect the friction of the air and I release it, it falls, and that's it. That is the simplest problem of dynamics. And when we study this problem with Newtonian mechanics, we need to apply Newton's second law of motion. Force is proportional to the time variation of linear momentum. But nowadays we say force equal mass times acceleration. F equals ma. And what is the force acting on the apple? It is just the gravitational force of the Earth, which is pulling downwards. And this is also due to Isaac Newton. And he showed that the gravitational force is proportional to the product of the two masses of the apple and the ears, and falls as the inverse square of the distance. So in this case, we have the distance is the radius of the ears. So the force is capital G, which is the universal constant of gravitation, mass of the ears, mass of the apple divided by r squared. At the right-hand side, we have ma, mass of the apple times the acceleration of the apple. So the mass of the apple cancels in the two sides of the equation. And then we obtain that the acceleration of free fall is capital G, mass of the ears divided by radius of the ears squared. When we plug in the numbers, the mass of the ears, the radius, and the value of the universal constant of gravity, we obtain the value 9.8 meters per second square. So this is the acceleration of free fall. So this is the simplest problem, okay? We are neglecting here air resistance. Now I will begin to show the problems. Even with the simplest problem of dynamics, the main problem is that in reality, there are no two-body problems in nature.
Well, they're approximated as two-body problems, right? We're like, so the moon is not involved in this.
Yes, we say the moon is not involved, the sun is not involved, the stars, Sirius, and all the other stars, they are not involved, and the galaxies, Andromeda, and so on.
Well, which makes sense, because like you never throw anything up in the air and then have it just like fly away towards the sun.
Yes, on the one hand it makes sense, but on the other hand, they are here. Mm-hmm. In reality, there exist no two-body problems because they are around us. Then we might say, well, the sun or the moon or a specific star or Andromeda, a specific galaxy, they are very far away. And according to Newton's law of gravitation, the force decreases as 1 over r squared. So the greatest the distance, the smaller the force. I agree. So the force of one star on the apple is negligible compared with the force of the ears, the weight of the apple. The force of one galaxy on the apple is negligible. But maybe when we add the force of all the stars, all the galaxies on the apple, it may have the same order of magnitude as the weight of the apple.
So wouldn't the apple not
Can
fall?
neglect one star, but not all of them.
Oh, the same
Yes.
order as the apple itself. I see.
Sorry?
So it would effectively double the mass of, or
Well, it's
half the
pulling-
mass
yeah.
of the apple.
Yeah,
Is that
because
what
it's pulling.
Yes. What is important is that we need to take them into account. And I myself, I believe that the universe is infinite. So there are an infinite amount of stars and galaxies. So the force of all of them on the apple might even be infinitely larger than the weight of the apple due to the Earth. So we need to take them into account. We always forget about it when we teach classical mechanics in high school, at the university, at graduate level. The textbooks, they don't mention it, but we need to, because they are around us.
So one thing that I don't follow is if the rest of the universe was exerting a force on the apple that was equivalent to the apple itself, this is what Shiloh asked. He was like, wouldn't it not fall if you let it go?
Not necessarily, because we need to calculate and see in which direction does it point and its value. So it might point downwards, upwards, I don't know, but we need to.
Can I just clarify that really quick? So he's saying it's not the same amount of force as the Earth on the apple, but as the apple on the Earth. Like the apple exerts a force.
It might be the same force as the ears on the apple.
I see. But then the apple wouldn't move.
Well, it depends. I think it depends.
If we're pointing upwards, upwards and the ears downwards,
like if you had like a 2-layer universe where, or I guess 3-layer universe, right? Like Earth,
yes.
You holding the apple, and then the
but
cosmos,
it's all over the place.
But because it's surrounding us, but if it's infinite, wouldn't the mass cancel? Right? Like if you have any point in the universe and all around it is homogenous and infinite.
Yes, Anastasia. If you were in the center, so by symmetry, it would cancel. Okay?
Is there a center of an infinite universe?
I don't think so. And but if the universe is finite, then if you were in the center, the force would cancel by symmetry. But if you are outside the center, it doesn't need to go to zero. Okay?
That's true.
The symmetry does not valid any longer. And it is amazing that we forget about the reminder of the universe. But Newton himself, he didn't. He did consider all the objects known at his time. He didn't know about the galaxies, but he knew about the stars. And in his book, Mathematical Principles of Natural Philosophy, he proved a very important theorem, which is theorem 30. He proved the following: if I have a spherical shell, and if I have a point particle inside the shell, but not in the center, but inside the shell, and each point of the spherical shell attracts the internal point with a force which falls as 1 over r squared. Newton integrated the force of the shell and showed that it goes to 0.
That makes sense.
And then due only to this theorem. So if we have many shells of stars and galaxies around the Earth, it doesn't matter, because each one of them, if I have my apple here, I have a star on the top, another on the bottom, one on the right, another on the left, and they cancel their mutual attractions. However, this theorem is only valid for forces which are central and which falls as 1 over r squared.
Okay.
It's not for every kind of force. If the force were, for instance, 1 over r, or 1 over r cubed, or exponential of the distance, or any other relationship, this theorem would no longer be valid. And in any problem, even in the free fall, we would be obliged to take into account the whole distribution of mass in the universe. So this is the first point to clarify. Later on, we can come back to this point, okay? So the first point is, in reality, there are no two bodies. Any two bodies, they are surrounded by a huge number of stars and galaxies. Only if the force is Newtonian, 1 over r square, can we neglect, not neglect, we integrate and show that it goes to 0, and then it is the same as if they were not there. So then we can go back to the earth and the apple. Okay? Now, second problem with this very simple experiment. F equals ma, the force is the weight, so the acceleration will be capital G, mass of the earth by radius of the earth square. When we plug in the values of the mass of the earth, radius, and the universal constant gravitation, we obtain that the acceleration of free fall is 9.8 meters per second square. So every student in mechanics learns by heart this number, 9.8, because it is the acceleration of free fall. So the second question, this is the acceleration of the apple relative to what? Well, we might think it should be acceleration of the apple relative to the ground. Newton said no. Why not? Because Newton did also study the motion of the earth itself. The earth orbiting around the sun, for instance, in elliptical orbits. So he cannot utilize the earth as his frame of reference because the earth is always at rest relative to itself. So he needs another frame of reference. So should we apply the sun? Newton said no. Why not? He didn't consider, but nowadays we know that the solar system orbits around the center of our galaxy. Maybe our galaxy, the Milky Way, is orbiting around another galaxy, and so on, and so on, and so on. So which frame of reference? This acceleration, 9.8, is the acceleration of the apple, relative to what? Newton, in the Principia, said that it is acceleration relative to empty space, the vacuum. He didn't utilize these words. His words were absolute space. But he said that absolute space has no relation with anything material. So it is the vacuum. But this is very strange because we don't see the vacuum. So how can I measure the acceleration of the apple relative to empty space?
It also is it's also bizarre too, right? Because the apple is definitely falling with respect to the Earth. Like if it was falling with respect to some external reference, it would just like stay behind as the Earth's cruising at what, like 70,000 kilometers per second or something crazy.
Moving around the sun.
Maybe not that fast. It's going really, really fast though. So yeah, the apple would just fly out behind you if it was moving.
The velocity, I believe, it is 30 kilometers per second at the surface of the Earth and so on. And
sorry, 70,000 miles per hour. There you go. So really, really, really fast. Yeah. And then the Earth is rotating, of course, too. And
yes. So the Earth has many motions, spinning once a day, orbiting once a year around the sun, and so on. So which reference frame should we utilize? So we need to follow Isaac Newton. And he said, relative to absolute space, which has no relation with anything material.
But I guess what I'm confused about, do you see what I'm saying? Like it's bizarre that Newton would say that if he recognizes that the apple is definitely falling with respect to the Earth. Like that acceleration is with respect to the Earth, right? Just empirically speaking.
Yeah, Shiloh, but if he did utilize the earth as his reference frame, he would not be able to study the motion of the earth itself.
So he wanted
because the earth does not move relative to itself.
he wanted to make he wanted to universalize this phenomenon.
Yes, he wanted only one reference frame.
Gotcha.
Because otherwise, when he's studying the motion of the earth, he would not need to utilize the sun or.
He'll end up with a series of two-body problems. He'll never be able to reduce it to like this universal equation.
And so he said absolute space, but it is empty space. Yes, Anastasia?
I have a small favor to ask. If you are enjoying the podcast, consider coming over to patreon.com. It is our exclusive funding model right now, and support from viewers allows us to maintain complete editorial independence. It allows us to not have to read you advertisements and interrupt you multiple times a podcast to tell you about what you should buy. And it's incredibly important that if you enjoy the podcast, you support creators of the kinds of media that you enjoy. So come over to patreon.com, donate a couple dollars a month, and help us keep the ship going. In order to be able to measure motion relative to absolute space, don't you have to have like a floating Cartesian coordinate system that's like marked absolute space in like the script of God?
But, sure. But the point, Anastasia, is that we don't see it. And so, but we need to have just like a blackboard so that we can say that but a blackboard is empty space. And so Newton, he knew that this concept of absolute space without relation to anything material was very problematic. But Newton was so great that he made an experiment in 1687 in which he proved that there is vacuum without a vacuum pump. They already existed in Newton's time, but in his experiment, I will do it here for both of you because this is just a fascinating experiment due to Isaac Newton. How he did prove the existence of the vacuum in 1687 without a vacuum pump.
Is it with burning something inside of a container?
No, it's just a bucket of water.
Okay.
So this is, I will repeat here Newton's bucket experiment.
That's some dirty looking water.
Yes, this is, I put Brazilian coffee, which is very good, just because it would be more visible. Okay?
I like that.
But Newton performed the experiment with plain water, okay? Tap water. And Newton's bucket was open. Mine is not a bucket, it is a shampoo bottle, okay? But inside it is air, it's not vacuum here, okay? I just opened it to put the water and then closed it, and there is a string here. So this is analogous to Newton's bucket experiment. So what is the experiment? When the bucket and the water, they are at rest relative to the ground, the water or the coffee is flat, okay? Then Newton did turn the bucket many times, and so the rope.
Here, can you lift it up just a little bit higher?
Yes,
there you go.
So Newton did turn many times, and then he did quickly spin it in the opposite direction. So this is the experiment.
And it's kind of crawling up the walls.
Yeah, so it becomes concave, okay? The faster it spins, the higher it goes along the walls of the bucket, okay? If it spins slowly, it's slightly concave, but if it spins really fast, it goes very high, okay? So this is the experiment. How could he prove the existence of the vacuum with this experiment? It's fascinating. This is Isaac Newton. So the question Newton asked was the following: why is the water flat here and concave here? Well, the obvious answer, because here it is spinning and it is concave. When it stops, it is flat. That's the answer. But then Newton's asked, rotating, spinning, relative to what? That is the crucial question. The water becomes, if we do the calculations, it's not very complicated. It is a parabolic shape, exactly parabolic. And it is proportional, the curvature is proportional to the square of the angular velocity. Okay? But spin, angular velocity, relative to what? That is the question. So I will discuss here 3 material suspects for the curvature of the water, for the parabolic shape. 1, rotation of the water relative to the bucket with whom the water is in contact. Second possibility, rotation of the water relative to the earth, the ground. And third possibility, rotation of the water relative to the remainder of the universe, to all other stars, galaxies, and so on. These are all the material bodies that we know: the bucket, the earth, and the remainder. The sun, the moon, the stars, the galaxies, Andromeda, and so on, to infinity and beyond. Okay? So let us discuss, is it the nature of the water is due to its rotation relative to the bucket? The first question. And this is a real experiment. Newton performed it, described it in the Principia, and said that he had performed the experiment. It's not a thought experiment. I am doing it here in front of both of you. So is it the curvature due to the rotation of the water relative to the bucket? Maybe. But then Newton argues that this is not the case. In the beginning, the bucket and the water, they are at rest relative to the ground, and the water is flat. Then Newton turns many times and releases the bucket. When Newton releases the bucket begins to spin relative to the ground, but the water is still at rest. But there is friction between the walls of the bucket and the water, and then the water begins to move in the same direction as the bucket. Then Newton said, there is a moment when the water is spinning together with the bucket relative to the ground. We can do it very easily, putting some bits of paper floating in the water, and then we see that the bits of paper go together with the bucket. So let us concentrate in this situation. In the first one, when both are at rest. In the second situation, when both are spinning together relative to the ground. In the first situation, the water is flat, horizontal. In the second situation, the water is parabolic. So Newton said, as there is no relative motion between the water and the bucket in the two situations, it's not the bucket the responsible for the curvature of the water. Because in both situations, there is no relative motion between the bucket and the water. So Newton eliminates the first suspect, material suspect. Then we say, okay, it's obvious that it's not the bucket because it's also very thin and so on. But we might say it must be the flattening, the curvature of the water must happen when the water is spinning relative to the ground. Because when it is at rest relative to the ground, it's flat, and when it is spinning relative to the ground, it is concave. But then Newton said, no, this is not the case. Why not? What is the force which the earth exerts on the apple?
You would expect it to be an upside-down parabola if that was the case, maybe.
Yeah, yes.
Like, because you would expect it to pull the tails of the water down towards the earth? Is that the idea?
Not only the tails, the whole ears. So what is the force which the ears exerts on the apple, which is the weight downwards? What is the force which the ears exerts on a molecule of water, which is spinning around the axis of the bucket?
Downward.
It continues to be just the weight downwards. So Newton's law of gravitation does not depend on velocity nor acceleration. So no matter the motion of the molecule of the water, the force of the earth always points downwards.
So basically the idea would be if it was the Earth when you spun the bucket, there wouldn't be a change in the way that the water looked.
Yes, the water should remain flat.
Got it.
Because the earth does not make a centrifugal force. The earth only pulls the water downwards, no matter the motion of the water. So Newton said, the curvature is also not due to the rotation of the water relative to the ground. Also, it happens when the water is spinning relative to the ground. But Newton said this is not the cause of the curvature, because the earth always pulls downwards. So Newton eliminates the second material suspect. So we have the third material suspect, the remainder of the universe. But then, what is the force of all the stars and galaxies on a molecule of the water when it is at rest? Do you remember I told about theorem 30?
It should be balanced, right? It should be in all directions, right?
Yes, they balance and they go to zero. And what happens when the water is spinning? What is the force exerted by all the stars and the galaxies in a molecule of the water when it is spinning? Once more, Newton's law of gravitation does not depend on velocity and acceleration, so it remains zero.
Okay, so then doesn't that eliminate all three causes then?
Yes, Anastasia. But then Newton said, yes, Anastasia, that's the point. But then Newton said, suppose that when I spin the bucket very quickly, that the water goes up to the border of the bucket once a second. If I did spin is twice a second or 3 times a second, the water would spill out of the bucket. Okay? So it is a real phenomenon. But then Newton said, it's not due to the rotation of the water relative to the bucket, not due to the rotation of the water relative to the ground, not due to the rotation of the water relative to the stars. But the effect is real. If I spin it very quickly, the water spills out. So Newton said, it must be the curvature relative to empty space, which he said, absolute space, but which has no material substrate, has no connection with anything material.
Okay,
It's
so
just fascinating. Just to, yes, Anastasia.
So if it is not a material cause and it is empty and it has no connection to the material, how does it exert a pull on the water?
Yes, this is a wonderful question. No one knows. And Newton did clarify it. But you see, Anastasia, with this experiment, without a vacuum pump, in the first place, Newton proved, at least according to his mind, that there is vacuum. In the second place, Anastasia, when you are spinning relative to this vacuum, there are real effects. The curvature of the water.
I guess I'm just not convinced that you have ruled out the entirety of the mass of the universe.
What else, Shiloh?
Well, I don't see, like, the way that I've always explained this to myself is through the connections to the rest of the universe. Like, if this water molecule, you spin it, it wants to stay put because it's connected to everything in the universe. And so it's going to by friction be like held, it's held in place inertially, right? By its connection to all the rest of the matter. And then as you spin it, it wants to stay in place and it's getting sort of dragged behind and it winds its way up the bucket this way. I don't see how Newton has distinguished between absolute space and the entirety of the universe, because things that are far sufficiently distant away may as well be static. They could be approximated as static.
Yes, but the point is his theorem 30.
So, but exactly in that, so that's assuming a homogeneous shelled universe that you're at the center of.
Yes. That's the point.
And so if you make that, if you make that assumption, that's correct, but you're saying that at rest, it's experiencing inertia that causes it to want to stay where it was when it was at rest. And as you spin it, what's the mechanism by which it climbs the bucket?
Well, it's being held in place, right? So there's some resistance to its motion. And then the friction eventually pulls it along, but it's still being held back where it used to be.
You are right, Shiloh. You need friction. As I said, in the beginning, when Newton releases the bucket, only the bucket spins, but there is friction. And then the water begins to move as well. But once both of them are spinning together, the friction is no longer necessary. And the shape will be parabolic. I can let them here spinning forever.
I guess
it will be parabolic.
But isn't that just because, all right, I know this isn't entirely an explanation, but go with me. The water molecules, once they reach a state of motion due to inertia, which is, I know, not an explanation, but hold on. But the inertia, the water molecules now have a state of motion that they are going to maintain unless something acts opposite to them, right?
Why doesn't the water stay flat then?
Because they're moving forward and they can't go anywhere once they crash against the wall of the buckets. They have to go up.
Moving relative to what? We go back to the same kind of question.
Relative to everything else in the universe.
Yes, but then, Shiloh, I agree with you. But then you are not a Newtonian.
Perhaps
you are a Machian.
Yes, indeed.
Yes.
Glad we got that out on the table.
Yes. And so let me continue. So Newton eliminated all the suspects. So with this experiment, he showed in the first place that there is empty space, and second place that when a body is accelerated or spinning relative to empty space, there will be real effects that we can measure. So the higher the water, you can know that it is spinning faster relative to nothing, which is very strange. But that was Isaac Newton. This experiment is so important that Newton put it in the beginning of the Principia, before his 3 laws of motion. Because it is this experiment which gives Newton something to hold on, to say, when I say force equal mass times acceleration, that acceleration is relative to what? So Newton said, relative to absolute space. But then people might say, well, but how can you know if you cannot see? Newton said, I cannot see empty space. I can discover when a body is spinning relative to empty space.
It's weird, though, because that can't possibly be true, given the fact that the apple doesn't fall off to the path of the Earth's orbit.
Yes.
If the apple was falling with respect to absolute space, like we discussed at the beginning, the apple would just trail out behind the Earth's orbit, right? The apple wouldn't fall.
You have to ask where absolute space is, right? That's the thing that's really a sticking point for me, because I'm looking at this.
Well, it's the backdrop upon which all these motions play out, presumably by definition.
Where, right? If I imagine the backdrop of absolute space, it needs to be some kind of location or volume.
Like the average of everybody's motion or something?
Yeah, where is this place? Because if you're talking about motion...
space is impossible to define without setting up some bodies, right? At least physical space, you need to have distance.
Yes, but This is why this experiment is so powerful. Because with this very simple experiment, Newton proved, at least according to his mind, that there must be this empty space, and that we know when we are accelerated relative to empty space.
So
By
do
the
you agree?
curvature
Do
of
you
the
agree
water.
with Newton's
No, not at all. Not
Okay,
at all.
okay.
Yeah. So
I think
so
that
I'm just giving
yeah.
the problems with this very simple free fall.
Sure.
And
And so I think that what you're the reason that you even point to this is that you're sort of astounded by the fact that he could even conceive of this idea of absolute space. Oh wow, that's really funny. It's my Zoom. I just did a thumbs up and it just showed. Did you see that?
yes.
So you're basically saying that it's astonishing that Newton in the 1600s was able to spin a bucket and then be like, "Hey, I think that there might be a vacuum."
Yes, yes.
Got it. But you're like, the vacuum is not the answer.
Yes, yes, because how can vacuum exert, as you said, Anastasia, how can vacuum exert, make the water do like that? Newton didn't explain it, but okay. But then no one could give an answer to Newton. Leibniz was against Newton, but he could not give an alternative explanation for the bucket. Bishop Berkeley was against Newton, but he could not give an answer to the bucket. But then, 200 years later, finally came someone. And this someone was Ernst Mach, M-A-C-H. Ernst Mach was an Austrian experimental physicist. We consider him as a philosopher of science, but he was really an experimental physicist. And he did need to begin to give classes to medical students after he got his degree. And when he began to prepare the material for these classes of classical mechanics, he found all of these problems. And Ernst Mach always loved philosophical and historical questions in physics. And he said, Newton must be wrong. It's not possible that rotation relative to empty space will cause a real effect in a body.
Because do you think he thought that way because he was so mechanically inclined? He really wanted a mechanical cause.
Not only mechanically inclined, Shiloh. I would say that he was very philosophically considering the problem. He said, in order to have motion, you need to have at least two bodies.
Yes.
So that they can approach or move away from each other. You cannot have the motion of one body relative to empty space.
Mm-hmm.
Only in our mind, but not in reality. So in order to have motion, you need to have at least two bodies. And so what did Ernst Mach say?
I would go even further, by the way, and say you can't even have a location without two bodies. And motion requires a change in location, but you have no location without some reference point.
Yes, sure, Shai. I agree completely with you. And so what did Ernst Mach say about the bucket? Ernst Mach said, okay, the curvature of the water is not, it happens not when the water is spinning relative to the bucket or relative to the ground, but when it is spinning relative to the stars, to the distant bodies. So this idea of Ernst Mach became known as Mach's principle. As you said, Shiloh, he didn't give this name Mach's principle, but later on people gave this name to him. But Mach went further. He put to all of us a fascinating thought experiment. So let us repeat Newton's experiment, and let's suppose that when the water is spinning once a second, that it goes up until the top of the bucket, okay? If it spins faster, it spills out of the bucket. Then Mach said, what will be the shape of the water if I let the bucket at rest relative to the ground and rotate all the stars around the axis of the bucket? And let's suppose that in Newton's real experiment, he rotates the bucket anti-clockwise once a second. Now we let the bucket at rest and rotate all the stars around the axis of the bucket once a second clockwise, so that the relative motion between the water and the stars is the same in both situations. Okay? This is a thought experiment. We don't know the answer, and we will never know the answer, because we cannot make the whole universe rotate once a second around my finger. This is impossible. It will ever be impossible. But we can consider this problem theoretically. What will be the shape of the water in Newtonian mechanics? So now the bucket, the water, and the ground, they are at rest, and all the stars and galaxies are spinning once a second around the axis of the bucket.
Well, it seems like Newton thought they would cancel out somehow, right?
Yes, that is once more theorem 30 of the Principia. So no matter if the spherical shell is at rest or spinning, Newton's law of gravitation does not depend on velocity nor acceleration. So the force on any internal body will be zero, no matter if the shell is at rest or spinning. So if you spin the stars and the galaxies, they make nothing in the water. So it will remain flat. And what will be the shape according to Ernst Mach? It will become parabolic. Because to Ernst Mach, the curvature of the water is due to its rotation relative to the stars. So it doesn't matter if you rotate the water or if you let the water at rest and rotate the universe in the opposite direction. As the relative motion is the same, the effect must be the same.
Why didn't Newton consider that position matters a lot? Like, I understand that velocity doesn't factor into his gravitational laws, but you're changing the position of the molecules of water, right? They're changing position.
No. In this case, the water is at rest.
Not with respect to the fixed stars, though, right? They're nearer or closer, different. Yeah.
Just the stars are beginning to rotate around the bucket, but the bucket remains at rest relative to the ground.
I guess I'm trying to unpack, what did Mach find to be Newton's error of logic?
He didn't say error of logic. He did say it is a philosophical mistake.
About the existence of absolute space that you can measure against, as far as I understand.
Do you see what I'm saying by any chance?
Not quite, but...
I mean, I'm just saying that, okay, Newton might be right that if something is at equilibrium, that it's held in place by everything equidistantly. Let's assume the universe is so big that it may as well be infinite. Even if it isn't infinite, it's huge. And you're basically at the center of this for all intents and purposes at any point, right? As you start to move the water molecules, you are changing their position, right? As friction takes over and they start to move, their position in that, yeah.
In this experiment, in this thought experiment, I'm not moving the water. I'm just moving the stars around the Earth.
No, I understand. I'm going back to Newton's experiment.
Okay, the original experiment.
Yeah.
Okay.
I'm just trying to explain how Newton might have conceived of the idea in a totally alternate universe that the distance relationship was changing with respect to each body in the universe as those waters moved.
It would be such a small, change, right?
But there's so many of them.
Of the water molecules?
No, of the body, of the other connections to the universe.
Yes, I agree, Shiloh, but the point is this theorem 30.
That
I understand. He got fixated
no
on
matter where
velocity.
you move it's not just velocity. Theorem 30 is the one that says no matter where you move something inside of a hollow sphere, it will experience zero force.
Because the gravitational equations don't depend on velocity whatsoever.
I think that in
Can-
this case, it's also the fact that all of the force vectors of a perfect sphere cancel everywhere in the sphere.
Can I read here Newton's theorem 30?
Yeah, let's do it,
let's do
please.
it.
Good idea.
Okay, I have it here with me. So I will read Newton's words in his book.
We should bring our
Mathematical
own
Principles.
Principia. We have a copy in the living room. We should bring ours.
Okay.
All of us
So
can follow along.
theorem 30. Words of Isaac Newton. If to every point of a spherical surface there tend equal centripetal forces decreasing as the square of the distance from these points, I say that a particle placed within that surface will not be attracted by these forces anyway. So this is a theorem. He proved it mathematically.
Does that make sense?
It is this theorem which allowed Newton to eliminate the influence of all the stars and all around the solar system and so on.
I guess what I'm trying to do is, I think that he's wrong about that. I think we kind of all think that he's wrong about that. And the question is, why didn't he see that? Like, why did this mathematical theorem trick him into thinking that it was the case when it wasn't the case?
Yeah, because if Ernst Mach is like, hey, if you rotate the stars, they will cause the water in the bucket to rise, that means that something about the theorem of the particle in the center of a sphere not experiencing any force is incorrect.
Yes, Anastasia.
Is that what you're trying to get
Exactly, yeah. And I want to know why it's incorrect.
to? Okay.
Yes, and both of you got the point. Einstein read the book of Ernst Mach, The Science of Mechanics, when he was in high school. And he was highly impressed by Machian ideas. Ernst Mach, in the preface of his book, he said that Newton's concept of absolute empty space is monstrous, is a monstrosity. He said, we need to get rid of this monstrosity in physics. And so he said, in the bucket, it must be the rotation of the water relative to the stars. And then he proposed this sort of experiment. But the experiment we cannot perform. But not only that, Ernst Mach didn't show where this theorem 30 might be wrong. But Einstein, he did like very much Machian ideas. And he wanted to implement the ideas of Ernst Mach. And then Einstein said, if we wish to implement this idea of Ernst Mach, that when I spin the universe, the water will be parabolic, then somehow we need to show that when we spin a spherical shell, there will be created inside of it real centrifugal forces, which will make the water do like that.
Okay, now we're getting somewhere. I think that this makes
And
less sense.
this is what Einstein tried with his general theory of relativity. He tried to implement Machian's ideas quantitatively, but he didn't succeed.
Okay, lay it on us. What went wrong?
So what was the goal of Einstein? He need to show that when you spin a spherical shell, you will create a centrifugal force which will create the parabolic shape. Einstein himself didn't make this specific calculation. The two scientists who made this calculation, utilizing Einstein's general theory of relativity, were Lenz and Tirring. It is called the Lenz-Tirring effect. So Einstein modified Newton's law of gravitation, introducing terms which depend on velocity, acceleration, and so on. And when Lenz and Tirring integrated the force exerted by a spinning shell on an internal test body, they obtained a centrifugal force, which would make the water goes to the sides of the wall of the bucket. But they also found an axial force pointing along the axis of rotation. So if we perform the calculations of this thought experiment that I spin the universe around a stationary bucket, according to Newton, it will become flat. According to Ernst Mach, it should become parabolic. According to Einstein's general theory of relativity, the profile becomes like a W letter. So because it has a centrifugal force, which puts the water sideways, but also an axial force, so it should become like that.
Like there should be a little hill at the center of the bucket.
Which must be wrong. Either it will be parabolic, as Mach said, or it will remain flat, as Newton said. But certainly it will not become a W, I believe. Okay? But so how can we implement Machian ideas? We need to include in Newton's law of gravitation components which depends on relative velocity and relative acceleration between the interacting bodies. Otherwise, we will go back to Theorem 30. This was done by Einstein in his general theory of relativity, and also by myself with Weber's law for gravitation in relational mechanics. Okay? So instead of Newton's law of gravitation, I apply Weber's law for gravitation, which is like Newton's law, but has also a component which depends on relative velocity and another component which depends on relative acceleration. And then we show that when we spin a spherical shell, inside of it there will be centrifugal forces which will make the bucket become parabolic. So we can implement mathematically the ideas of Ernst Mach, not with Einstein's general theory of relativity, but with relational mechanics and Weber's force law for gravitation.
And what's the significance of Weber's force law for gravitation here?
Because it is, this force was developed by the German physicist Wilhelm Weber, who worked together with Gauss in 19th century, and he proposed this law for electrodynamics in order to unify the laws of Coulomb, Ampère, and Faraday.
And so how does that relate to the rotational motion then?
Because if you apply the same law because Weber's law is just like Coulomb's law, Q1, Q2 over R square, which is just like Newton's law of gravitation. But we know that in electrodynamics, we need forces which depend on relative velocity and relative acceleration. So the idea is, let's come back. Why not, if this force is so powerful in electrodynamics, why not to apply it to gravitation as well? And when we apply that, then we implement Machian ideas. But before going to discuss these ideas and so on, if you allow me, I would like to discuss another experiment
Yes, please.
to also to clarify Machian ideas.
All right, before we go there, though, let me just so usually when kids learn about the invention of general relativity, they learn that the equivalence was made by Einstein between inertia and gravitation, right?
Yes.
And so, in some sense, this is attributed to Mach's principle that Einstein was following Mach's lead. Where did he go off the rails? Like, what happens that leads him not to arrive at the correct solution?
Because he didn't begin with a force law which depends only on distance between bodies, relative velocity, relative acceleration.
So the fact that he doesn't involve motion in his conception of gravity and inertia is a problem.
No, he does involve motion, but motion of the bodies relative to space, just like Newton.
Really? Okay.
Yes. That was when he got wrong.
That's so bizarre because it's called relativity. You would think it would be...
Yes, Shiloh. And for this reason, I gave another name, relational mechanics, because it is against Einstein. I don't believe in Einstein. I'm fighting against Einstein.
That's really interesting.
Also against Newton.
So Einstein's absolute space becomes space-time, essentially? That is becomes the concept of space-time.
In Einstein, yes, not in relational mechanics.
And it's very similar in spirit to Newton's absolute space.
Yes, the Einstein's general theory of relativity, yes.
But that's so bizarre if he hated
Shiloh.
Yeah.
It introduced another absolute concept, which is light velocity.
Right.
Which is the same for all observers, for all sources, and so on. So it is even more absolute than Newton.
Which is interesting, because didn't you say that Einstein he said it was like a plague on science or something?
No, that was Mach in the introduction. Said that the absolute space.
I see. Okay, that makes more sense.
And it is also interesting because Einstein was so inspired by Ernst Mach.
Yeah.
That Ernst Mach was his hero, and Ernst Mach was alive when Einstein was developed his special. And when he was developing his general theory of relativity. In 1913, he already had essentially his general theory of relativity. And he paid a visit to Ernst Mach in Wien, Austria. Ernst Mach was there, he received Einstein, and so on. Then Einstein sent some letters to Ernst Mach, which exist, have been published, and so on. But then, in the last published book of Ernst Mach, The Principles of Physical Optics, in the preface, Ernst Mach said, "From what I hear about the theories of relativity, they say that they are based on my ideas." But he said, "I do not agree with this theory. They do not represent my ideas." So he was against Einstein's theories of relativity as Einstein and the publications arrived at him. So he rejected them. Is there any record? Einstein was inspired by them.
Is there any record of Mach's replies to Einstein's letters, or do we have any sense of the discussions, like Mach's, let's say, output?
I'm not sure, but I know that this publication, it's very clear. And when this book was published, then Einstein became against Ernst Mach. He was a poor philosopher and so on.
Oh, wow.
And then, then from that time onwards, the textbooks on relativity, they say, well, Ernst Mach was important just for inspiring Einstein. But
Right.
then you can forget about Mach's principle. Why you can forget? Because Einstein's general theory of relativity does not implement Machian ideas.
Got it.
A body, this apple, in empty space has inertia in Einstein's general theory of relativity, which should not. Because if inertia comes from an interaction, if it were aligned, it should have no inertia. But it has in Einstein's general theory of relativity. So it is not Machian.
Interesting.
He wanted it to be, but he didn't succeed.
That explains why it's so confusing how most introductory textbooks kind of mention
Yes.
Mach's principle, but they're also just kind of move away from
But
it
it's
really quickly.
sideways.
Yeah.
Yeah.
That's really
Because,
interesting.
okay, it was important for inspiring Einstein, but then forget about it. It is just a philosophical idea and so on. The important are the equations and so on.
I mean, the reason this really appealed to me when I first learned about it was when I was trying to understand inertia. Because, you can take, if you are an astronaut in space and you have a bowling ball, you might think everything is weightless, so the bowling ball is really no problem. Right? But it turns out that actually the bowling ball is still really hard to change the trajectory. You have to move it, you have to apply the same amount of force. It's actually very difficult to move heavy things. And so the easiest way to explain that to yourself is, for me anyways, is this Machian idea that the bowling ball is attached to everything, actually. And so, of course, the bigger, the more massive, the more attachments it has to everything. And then you can sort of understand, at least in so much as you understand gravity, you can understand inertia. And that's really comforting to me.
Yes, sure. I agree 100% with you, Charles. Because as I said, in your thinking, you are a Machian.
Yeah.
From the beginning. You are not a Newtonian. But most people, they are Newtonian because that's what we learn.
I see. Yeah, I'm glad you clarified that for me. That's been a little bit of a blind spot I wasn't aware of. I just always had the idea that because Einstein was inspired by Mach, that he didn't hang on to this idea of absolute space. But I can see now that space-time itself
continues there.
Yeah.
It continues there.
Yeah,
yes.
That makes sense. It's really interesting.
As I said, this apple alone in the universe has inertia in Einstein's general theory of relativity.
Right.
But inertia relative to what? If there is no stars, galaxies, airs, nothing. It cannot have. But it has in Einstein's theory. Not in relational mechanics, but...
Nice. All right, so
there was another experiment. Yeah, let's do it.
Okay. This is also due to Isaac Newton. Okay. We say that for 2,000 years, we believed that the Earth was at rest in the center of the universe, the geocentric world of Ptolemaios. Then came Copernicus along and said, no, the sun and the stars, they are at rest. And the Earth spins once a day around its axis and orbits once a year around the sun. Okay? But Copernicus could not prove these motions of the Earth. We don't feel in our bodies the spin of the Earth nor the orbit of the Earth. So for most people, it was strange. And Galileo, he was in favor of Copernicus, but he could not prove the motions of the Earth. He tried, but he couldn't. But then Newton came along, and Newton could prove that the Earth, in fact, spins around its axis. How could Newton prove that? We go back to the bucket. If I spin the bucket, the water goes to the sides, okay? So anybody which is spinning tries to move sideways, away from the axis of rotation. There are centrifugal forces acting really in the body. So now I will make an experiment about the rotation of the Earth.
Hey, quick interruption. We are getting really, really close to our first live event in Austin, Texas on April 7th and 8th, and I would love to see you there. It's going to be a really tight weekend of talks, workshops, discussions, beer drinking, whatever you love. We're going to hang out and work towards how to get closer to the bottom of a lot of these mysteries we explore on the show. And we're going to do it in person. It's going to be really, really incredible. And there's a total solar eclipse, which isn't going to happen again for quite a while, several decades anyways. So now's your chance, and I want to see you there. You can grab a ticket up here.
Here is my Earth. So I have an axis here, and I have these metallic strips, okay? And at the top, it is fixed here, but in the bottom, it can move. Okay, it can slide on the axis. But
So
here
you can
on
sort of,
top, it is...
just to describe it for people who are listening, it has like a structure that has these bowed, it's almost like a wireframe version of a sphere, but he can squish the sphere and make it sort of flat-ish versus spherical, something like that.
So, for instance, it is spherical here. It will represent the ears. But I can flatten it with my hand, doing like that.
By pushing on the bottom of it.
Or doing like that.
By pulling on the sides of it.
Yes, I can pull on the side, or I can press it from top and bottom.
Mm-hmm.
Who is flattening the ears? My hand. Okay? In this case, I can press top and bottom, or I can pull on the side. Okay? Who is responsible? My hand. Now I will also flatten the ears without touching it. How can I do that? Just spinning it. I hope, I don't know if you can see it, but when I spin it, it becomes shorter along the axis of rotation. The faster I spin, you see, it becomes more.
Yeah, and because you're going back and forth, it basically like goes back through the 0 points, but it's
so
small
it
at
back,
each.
Because here I cannot make it spin only in one direction.
Right.
In my lab, I can do it because I fixed that with a handle. Then I can spin only in one direction, so I can control.
Sure. But basically, the faster that you spin
it goes in both directions.
But the faster that you spin it, the narrower it gets.
Yes.
And the more oblong it gets.
So this...
Oblate.
Yes, it becomes oblate, yes. So, and so what is the relation of these with the ears? Because the ears is not a solid body. The ears, despite the name, is full of fluids, water. And maybe in the history of the ears, it was completely fluid in the beginning. But if it were spinning, these centrifugal forces should be acting on the ears. And Newton, in the Principia, he made a very complex calculation of the shape of the ears due to its diurnal rotation once a day. He made the calculations and he concluded that the equatorial diameter of the ears is to its polar diameter as 230 divided by 229. If we make this ratio, we will obtain 1.004. That is, the flattening is very small, 0.4%, but it is not zero. And where does it come from? From the diurnal spin of the ears. Okay? So this was Newton in the Principia. At that time, no one had measured this flattening of the ears. And there was another theory due to the vortices of René Descartes and the Dutch physicist Huygens. They believe that because of this vortex of an ether around the ears or the ears around the ether and so on, the ears should be flattened at the equator. So according to Huygens, the ears should be like that. According to Newton, it should be like that. Okay? So 50 years after the publication of the Principia, Newton's death, and so on, astronomers did travel all over the world by the French Society of Physics and so on, measuring the meridian of the Earth. And then they concluded that the Earth is flattened at the poles, like Newton said, and the amount was 0.4%, just like Newton had calculated, which is a very complex calculation, because not only you have the centrifugal force, because the centrifugal force already creates this oblate shape, but the fact itself that the Earth is oblate creates another factor for increasing the oblateness of any liquid portion of the Earth. So we have two components. It doesn't matter. The point is that it is flattened at the poles. So according to what this has this flattening to do with Mach's principle? Because according to Newton, the flattening happens only because the Earth itself spins. If the Earth were stationary here in my hand, and Superman goes there and spins the whole universe once a day around the Earth, what will be the shape of the Earth?
Well, according
like
to
the
Newton,
bucket.
round, yeah.
According to Newton, round. According to Ernst Mach, it should be flattened. Okay? Unfortunately, we cannot do this experiment. If we could know who is right, Newton or Ernst Mach. But yes, Anastasia?
Is this an experiment that can be done in, let's say you had a lab in zero gravity and you could take a deformable liquid and put it inside of a heavy sphere and then spin the sphere and see what happens to the liquid?
You are right, Anastasia.
Okay.
Yes. Both of them. I can do a real experiment with this one here. I cannot spin the whole universe, but I can put a glass shell around this deformable body here. And I can spin only the shell relative to the ground. These I can do.
Has anyone done that?
Yes.
Well, it'd have to be a really, really heavy shell to approximate the mass of the entire universe.
I will not tell the answer, but these kinds of experiments, not exactly these, but this kind of experiments have been done. But you see, this is fascinating, Shiloh and Anastasia, because up to now I'm talking about philosophy. Or if you spin the whole universe and so on, we cannot do that. So, if you, instead of spinning the bucket, if I spin the universe, this I cannot do. But these philosophical ideas, they lead to real experiment. I can put these two bodies, the water and my ears, inside a glass shell. And I can spin the glass shell around my bucket. I can spin with my hand the glass shell. The bucket remains at rest relative to the ground. What should happen according to Newton with the water? Nothing. What should happen according to Ernst Mach? It should become slightly parabolic.
It would have to be really heavy.
It would have to be very heavy.
Yes, but both of you are right. You got the essence of Mach's principle, because the effect should be there, but should be very small, because the mass of the glass shell is very small compared with the universe. But the higher the mass of the glass shell, the higher should be the effect. And the important point is that we can do this experiment and we can do calculations with different theories. If we do calculations with Einstein's general theory of relativity, What will be the shape of the water? The W. But a very small W. What will be the shape with relational mechanics? Parabolic. But a very small parabolic. And if we do a real calculation with a glass shell of 1,000 kilograms of a radius of 50 centimeters, spinning once a second, the amount that the water will go up at the border here is 10 to minus 27 meters. It's not even one atom. So it's nothing. But you see, these philosophical ideas, they lead to real experiments. And we have different theories giving different mathematical predictions, which is fascinating. This is why physics is so fascinating, because we mix history of science, philosophy, real experiments, mathematics, calculations, and we can go to the lab and test these ideas. This is fantastic.
Yeah, do you have any idea, like, what size of mass would you need to actually see something appreciable? Like, something optically, something measurable?
Yes.
How big
People
would it have to be?
are trying this kind of experiment, not putting a spherical shell around the bucket, nothing of this kind. What they are doing really is the following. They put a test body, like a bucket, but not a bucket, in a satellite. But in a satellite that is a satellite, which if you are in the satellite, you see the Earth spinning. Mm-hmm. And according to Einstein's theory of relativity or relational mechanics, a spinning Earth should generate in the satellite a small centrifugal force, a small Coriolis force, and so on. And in this case, it's not a glass shell, and the distance here is not so great. And now, instead of putting a bucket, they would put a bucket in the satellite, but instead of a bucket, they put a gyroscope. Mm-hmm. So they put a gyroscope pointing along a specific star.
Is this the gravity probe? Is this the gravity probe B experiment?
Gravity probe B, exactly, Anastasia. So they see if the rotation of the Earth affects the direction of the gyroscope.
And
in this case, Shiloh, the calculations with general theory of relativity or relational mechanics and so on is 1 part in 10 to 10. Not 1 part in 10 to 20, like a glass shell around the bucket. But 1 part in 10 to 10, and these we can measure. And so people are trying these kind of experiments nowadays. This is just fantastic. So in a few years, we should have some outcomes of these results.
Do you think that it will actually force people to reconsider the underlying assumptions of general relativity if this proves out,
so.
or or will they just explain it away some other way?
Wikipedia says that
so.
Wikipedia says that it's in good agreement with the predictions of general relativity as according to 2011, but I'm suspicious why the last record on this is 2011. So
Let me just go back here to the flattening of the Earth, because as I said, according to Ernst Mach, the flattening will be the same, no matter if you spin the Earth or if you let the Earth stationary and spins the Earth in the universe in the opposite direction. Let me put here another question, which was put by Carl Neumann, a German mathematician, in 1869. So the Earth spins once a day, and it is flattened. 0.4%, but it is flattened. So the question of Carl Neumann was the following, very interesting question. What would be the shape of the Earth if it were possible to annihilate all stars in the universe, if the Earth became alone in the universe. Okay?
I suppose a perfect sphere.
According to
Newton.
yes,
Well, I guess
and
according to everybody.
No.
Oh, no, because, yeah, sorry.
Oh, because it's been
a perfect sphere according to Ernst Mach.
To Mach, yeah, because Newton would say that the deformation of the Earth comes from the Earth itself relative to absolute space, but for Mach, it's the deformation relative to
the Earth would remain spinning relative to empty space. So his theorem 30, you can increase the amount of stars or decrease the amount of stars without affecting anything in the solar system. So according to Newtonian mechanics, if there were only the Earth in the universe, you could somehow say that it is moving, and the amount of motion relative to nothing.
So,
according to the ideas of Ernst Mach, it does not make sense philosophically to speak the motion of the Earth if we are alone in the universe. So if you cannot talk about the motion of the Earth, all the effects that might originate from this motion should disappear when you disappear all the stars in the universe. Yes, Anastasia?
Sometimes all of the planets align in the solar system. And that's kind of like a momentary magnification of the pressures that the Earth experiences. Is that enough of a pull to have a detectable change on the oblateness of the Earth, or is it just too brief?
With gravitation, I believe that that's very, very small, very difficult. But
because of the inverse square law, it just falls off so incredibly strongly.
I know, but we're talking about like the whole of the universe affecting
possibilities.
us.
These are possibilities. Yes, if there were the whole universe aligning, then that would be a huge effect. But a single planet aligning, so that's very small.
Well, I'm just thinking, like, let's say, is there ever a time where there's the alignment of multiple celestial objects? Like, let's say there is all of the planets align with the Earth and the Sun, and then, like, the closest star also aligns, and then the closest galaxy also aligns. Like, those just don't.
That doesn't happen, yes. If it did happen, it might have an effect, yes. But in reality, it doesn't.
Because there is some weak isotropic, like, cosmological principle here that everything is essentially homogeneously distributed, more or less.
Yes.
Isn't that like kind of like questionable? Aren't they finding all of these weird structures that aren't supposed to be there, and they're kind of like, well, maybe it's not homogeneously distributed?
No, it's not completely homogeneous, and these tiny effects due to these anisotropies, we can detect some of them.
Are you aware of the axis of evil in cosmology? Have you heard of this term?
Yes, I heard of it.
This is kind of interesting too, because I think it's related in some sense, because when they first did these maps of the CMB, they saw the Earth had some Doppler motion relative to the CMB. And they thought, well, this might be in some sense, it reinforces this absolute space because but then they start to find that those motions aren't commensurate with our optical motions with respect to different galaxies and supernovas and so forth. And so this background, this motion doesn't seem to make sense at an absolute if you treat the CMB as the absolute space, this doesn't really work out, which is quite fascinating.
Yes, but all of these measurements, they are still somewhat new, so we need to go slowly with all these statements that we see in the press, because nowadays so much novelties all the time that we need to go slowly. But what I want, yes?
What's our mechanism here? Like, if gravity falls off with the inverse square of distance, then the effect of the rest of the universe gravitationally should be negligible at that distance.
Not
right?
Because it's just such an overwhelming amount of material.
It's just
like if you talk about a couple of planets, it is negligible.
But basically, like the M2,
everything, like literally add up all of the other connections. Even if you have one connection to like a distant body, it's going to add up over all that distance. Essentially, you just have so many of those bodies, like I mean, he's using this idea of an infinite universe, but for all intents and purposes, we can as far as we can see, there's stuff.
Well, because I mean, like you'd integrate it across distance basically, and so it's like the m2 term in the gravitational equation would be so big that it doesn't matter that r squared is enormous.
Yeah.
So yes, but the point which I want to come back is that this question of Carl Neumann, he put this question, and he was a Newtonian. And to him, it was obvious that even if you annihilate all the stars in the universe, that the Earth would remain spinning and would remain flattened at the poles. But if we do the calculations, and that's very interesting, if we do the calculations of the flattening of the Earth in relational mechanics, then we always need to integrate over the whole universe. That theorem 30 will no longer be valid with Weber's force for gravitation. And when we do perform the calculations, we obtain that the amount of flattening of the Earth depends not only on the relative rotation between the Earth and the distant stars and the galaxies, but is also proportional to the mean density of matter in the universe. So that when we make in our calculation this mean density of matter in the universe goes to zero, like annihilating all the stars and so on, the Earth, instead of becoming like that, becomes spherical.
Makes sense.
So this is fascinating because we can implement these Machian ideas mathematically, which is very interesting. Very, very interesting. For instance, if I go back to the free fall of an apple here, when we do the same calculations with relational mechanics, this acceleration of free fall, it is proportional to the mass of the Earth. For instance, if I go to the moon, the acceleration of free fall is 1/6 that of the Earth, because the mass of the moon is much smaller than the mass of the Earth. It depends also on the radius. But if we do the same calculations with relational mechanics, we obtain that the acceleration of free fall depends also on the mean density of matter in the universe. So this 9.8 meters per second square is not only a function of the apple and the ground. In relational mechanics, it is also a function of the mean density of matter in the universe.
Which should be constant, right? More or less? Is this
yes,
just
so.
Factored into the gravitational constant or something?
Yes, Shiloh, exactly. We obtain that the so-called universal constant of gravitation, the capital G, in relational mechanics, it should be inversely proportional to the mean density of matter in the universe. So it should be a function of the, in any theory which tries to implement Machian ideas, we always need to take into account the distribution of matter in the universe. Literally, we cannot consider any longer any two-body problems.
That complicates things.
Yes, it does.
It also gets really squishy too if you imagine that like if you have a cosmology where the universe is denser at some point in time, then you would have different mechanics at that point in time.
Yes, exactly.
Now, I personally don't subscribe to that, but that is a part of standard cosmology, right? that you should have a denser universe at some points in the past.
I don't subscribe to that either, Shiloh, because I don't believe in the Big Bang, in the expansion of the universe, in a finite universe, and so on. To me, the universe is infinite in all directions, has always existed, and I hope it will always exist in the future. And to me, the Hubble's law is due to an interaction of the photon which left a distant galaxy in its journey until it arrived to the Earth, not due to Doppler effect. To me, it is simply due to interaction. So,
do you think that there's an experiment that could separate that out? Like, do you think you could do an experiment to actually show photons losing energy due to relay? Like, due to all of these interactions along the way? Is there a way to untangle those effects? Because as far as I know, like, yes, that seems completely reasonable to me, but it seems like nobody has thought of a way to show that in a laboratory, that kind of tired light is possible.
We know many phenomena which create redshift.
Sure.
The Doppler is just one of them. We have gravitational redshift. We have
condensed matter chemistry can do it too. Like interactions with molecules.
A Compton effect, for instance. We have a photon which reaches a free electron, scatter. So the electron received energy. So the photon lost energy.
The problem with that one is always that it's sort of this chromatic, right? It depends on wavelength, right? And so I guess nobody's really managed to convince people that all of the wavelengths are affected.
Yes, I agree. But the point is, any kind of interaction will decrease the energy of the electromagnetic radiation.
Right.
Any kind of interaction will create a redshift. And we know other kinds of redshift beyond Doppler, and that's the point.
But most of them are chromatic, though, from what I understand. I guess it's like nobody's convinced the wider scientific community that there's an achromatic process to cause redshift other than Doppler.
But you see, Shiloh, Hubble himself, he didn't believe in the Doppler interpretation. In his original paper of 1929, when he arrived at the so-called Hubble's law of redshift, that the redshift is proportional to the distance and so on, he talked about the de Sitter universe and Doppler interpretation and so on. But later on, Hubble himself began to obtain very high values of redshift, which would mean very high velocities.
Increasingly, like an acceleration at distances, something like that.
Not necessarily acceleration, but very high velocities compared with light velocity. And so he began to be suspicious about it. And for the last 20 or 30 years of his life, he was trying to find another mechanism. He couldn't find it, but he began to write apparent velocity, not real velocity, between quotation marks. And he proposed some tests with Richard Tolman of Caltech and other places. And so Hubble himself, he was very suspicious and against this Doppler interpretation of his own law.
Just because he didn't think that those bodies could be moving that fast relative to us.
Yes, because he said the only bodies which move that fast are light itself or very small particles like electrons, ions, but not a whole star or a whole galaxy. That didn't make sense. So he did prefer an infinite universe without expansion and without Big Bang.
Was it really just the discovery of the microwave background that it really became widespread, that people adopted that expansion interpretation of the Hubble data?
But you see, Shiloh, even the cosmic microwave background, when we look at the history of the cosmic microwave background, the first calculations based on the Big Bang was from 19...
Like the 40s?
49, I guess,
Yeah.
by two students of Gamow,
Right.
Alpher and Hermann. And they said 5 Kelvin. Then they published a second paper and they said higher than 5 Kelvin. Then Gamow in 1953, he published a calculation and obtained 7 Kelvin. Then in 1961,
And by the way, this is all just based on how this radiation should cool given the age of the universe from the Hubble time.
yes, Gamow and his students, he was working in the paradigm of the Big Bang. Okay. Then in 1961, just 4 years before the discovery of the cosmic microwave background, Gamow did publish a book called The Creation of the Universe. Even the title is religious. And in this book, Gamow made the calculations and arrived at a temperature, if I'm not mistaken, 50 degrees or so.
I'm sorry.
Then 4 years later, they did find 3 degrees. You see, they began with 5, greater than 5, 7, and 50. Then they discovered 3. And they said, oh, we had predicted that. That's wrong. But worse than wrong, if we look at the history of the predictions of the temperature of the microwave background, we see that people working in the paradigm of an infinite universe without Big Bang and without expansion did predict better and before Gamow. The oldest prediction was made by a Nobel Prize winner, Guillaume. He published that in French in 1896. He did measure the background light of the galaxy, the background stars. And he did utilize Stefan Boltzmann's law, which says that this energy is proportional to the force power of the temperature. It was a measurement. And his paper is called The Temperature of Space. It was published in French in a journal called La Nature. And he did obtain 5 Kelvin. Gamow was not even born at the end of the 19th century. And this Guillaume is so important that he received the Nobel Prize a few years later for his high precision measurements. He did discover some substances which deflect depending on the amount of temperature and so on and so on and so on. Later on, we have Wegener. Wegener did publish 1933, many years before Gamow. Wegener was one of the pioneers of cosmic radiation, of the cosmic ray radiation. And this Wegener, in 1933, he did obtain a temperature of 2.8 Kelvin based on measurement of the cosmic ray background. Then in the same year,
and this is all just based essentially on the mean radiative power of stars and the density distribution and so forth.
No expansion, no Big Bang, nothing.
Yeah, that's really interesting.
And then Ernst, the father of the third law of thermodynamics, he proposed an exponential law of the Hubble's law and so on. And he arrived also at 5 Kelvin. But the standard textbooks, they don't mention these things. But you see, I published this a few years ago. A colleague of mine, Roy Keyes, made a translation of this paper by Guillaume, and it is now published in the American Journal of Physics. So it was much before Gamow and his students. So all of these people, they did obtain temperature much closer to 2.7 Kelvin than Gamow and his students, and much before Gamow. Also, this does not appear in the textbooks, but these are historical facts. And very important people, the Nobel Prize, Guillaume, Wegener, one of the most important pioneers of cosmic ray physics.
How do you spell that, Guillaume? Sorry, I want to look into this one because I want to bring this to my students.
Guillaume.
Okay.
If you just put Guillaume and the American Journal of Physics, in my homepage, there is a link there for this English translation of this paper.
Great.
1896.
All right. Can we, all right. I want to land this conversation and wrap this into something. Do you think that we could take a quick bathroom break though, really quick, and just fill our tea and
good idea.
All right. So
I give a quick look. If later on you put the link of my homepage in the description of this conversation, I published a paper in 2009. The title is Hubble's Cosmology: From a Finite Expanding Universe to a Static Endless Universe. So anyone looking at the link of my homepage can just go in the papers and find this paper there. And there I present many quotations from Hubble himself, showing how he changed his mind from his first paper, 1949, when he presented the Hubble's law, that he assumed that the redshift was due to Doppler, motion between the source and the detector. And then he changed his mind because he was obtaining higher and higher values of redshift of galaxies, which are huge objects. And he said, this cannot be the case. So he said, we need a new principle of nature, which will explain this redshift in an infinite static universe. And he said, simpler, the universe which has always existed without expansion and without Big Bang. And he believed in this universe without Big Bang until his death. Okay.
That's really interesting. I'm going to read that tomorrow because I actually have to I have to give a final lecture for my course to wrap up this cosmology business on Thursday. And so I'll be very interested to read that. So thanks for sharing that.
That was a paper which I presented in 2009 in USA in a conference, Cosmology Back in Physics, CCC2 conference, 2009.
Do you have a sense of why people jumped on board with the expansion universe? I mean, it seemed like
because of the religion. I have no doubt of that. Because people need a creator, they need something like that.
But science was, for so long, it was at least in the 19th century and so forth, people were really opposed to the act of the creator in science, right? It seemed like people.
Yes, but
what happened?
You see, Shailen, if you see the people who created this Big Bang cosmology, some of them they were priests, and so
Lemaitre and so forth. But why did it change? Like, I guess I'm very confused about this in the history of physics because it seemed like most people had this eternal conception of the universe from a scientific perspective before the early 20th century, and then they changed their mind all of a sudden. And do you think it's just because the science became, let's say, the church actually became less prevalent of a force in people's lives in the 20th century, and so they needed to look to the scientists to give them that sense of God all of a sudden? Like, why do you think that it appears all of a sudden in the 20th century?
Well, I don't know. I believe it is because most people, even many scientists, they have this religious background and from different religions, but most of these religions, they have a beginning, they have a creator, and the Big Bang gives something of this kind. It's not that the universe was created 6,000 years ago, but 15 billion years ago. But in the end, it is the same. You need a creator there, and so
it's
I
like they
believe
can sort of you move it back far enough so it remains in the realm of science, but you can still keep the creator force, basically.
Yes. But you see, to me, this never made sense because this creation out of nothing, it is against the most basic conservation laws of physics, which is conservation of matter and conservation of energy. How can out of nothing something appear and so ordered? So to me, this never made sense. So
I had trouble with this since I was a little kid too. It's just there's never a very good mechanism given for it. That's what it really comes down to.
It's not. How can out of nothing something appear? It doesn't make sense to me. It doesn't make the least sense. So I don't know. To me, I don't know why the universe exists, but I see it is there. So it's simply that it has always been there, and I hope it will always be there. And I hope, happily for me, I can now work in science with this infinite universe without creation, without expansion, without dark energy, without dark matter. All of these, to me, these are simply mysticisms. All of these things, I don't know. The other paper, which I was talking here about Guillaume, I just gave a quick look in my homepage. I did publish this paper in the American Journal of Physics in 2020. The title is Complete and Commented Translation of Guillaume's 1896 paper on the temperature of space. So it was published originally in French. Now we have a complete translation in English with comments and so on. And to me, this was the oldest guy who obtained a temperature of space. This is the title of his paper, 1896. And he obtained 5 Kelvin. It's amazing. And it's not just calculation. He's measuring the background stars, energy of the background stars, applying Stefan Boltzmann's law, and obtain this temperature. Without Big Bang, without expansion. So the cosmic microwave background, instead of being a proof of the Big Bang, is a proof against the Big Bang. Because people working with an infinite universe without expansion did measure it before and better than the people working in the paradigm of the Big Bang. But this is not mentioned in the textbooks because most of the textbooks, they work in this paradigm of the Big Bang. But if you read the original papers by Guillaume, by Ernst, by Wegener, by de Broglie, by many others which I quote there, they all published before and better than the Big Bang this 3 Kelvin radiation. Even one of them, I forgot the name now, but it is another Nobel Prize. It was when he was discussing this paper by Wegener. He said, if this mechanism is at work, so it should be connected with radio waves. Before the discovery in 1965 by Penzias and Wilson, utilizing a radio detector, radio antenna. You see, these are real predictions. People working without Big Bang. without expansion, with an infinite stationary universe. But this does not appear in the textbooks. But
No, it
these
does
are
not.
facts.
All right, so in the spirit of demystifying physics here, so by getting rid of the mysterious universal background reference frame, we at least have a relational mechanics where one body is influencing another. But
Yes.
there's still this piece of supernaturalism inside of it, which is that there's this force, this gravitational force.
Yes. Yes.
Do you spend any time thinking about the cause
A
of
lot.
that force? Okay.
A lot.
Okay.
Since my undergraduate studies, Shiloh. But up to now, I could not find a mechanism. I believe that when I was in undergraduate studies, if I have here my two buddies, né? It can be the apple, the ears, and so on. And I said, how can one affect the other at a distance? So I remember that I said, well, maybe the ears emits some particles, real particles. And these particles, they travel, and when they reach the other object, somehow they interact with them and make it move towards the ears. That was one of my first ideas. And then I said, oh, if this is the case, if this pen is moving at the same velocity as these particles, little particles, the particles will not reach it. So it will not be attracted. And if somehow the pen moves faster than these small bullets, it will be attracted to the right, away from it. And so, that was the beginning, how I thought that maybe the force depends on velocity between the two bodies. But later on, I gave up this mechanism because it didn't work. But it was how I began to think about forces depending on velocity and acceleration. And later on, I arrived in Weber's force law, which has also been forgotten, completely forgotten. It was the main theory of electrodynamics of the 19th century. Weber did work in Göttingen together with the great mathematician Gauss. They create the absolute system of units. Weber did unify Coulomb, Ampère, and Faraday 20 years before Maxwell. But then, at the end of the 19th century, the paradigm changed. And then Weber was suddenly completely eliminated from the textbooks. And we remained only with Faraday and Maxwell and Lorentz and Einstein. And then Weber was never translated. Ampere, that we talk so much, Ampere, which has a unit of current. Ampere, we say, oh, Ampere circuital law, as I said in our other conversation. Ampere never wrote such a circuital law. In his first page of his main book, Ampere was fighting against the idea of anything circulating around a current carrying wire. He said, no, Newton taught us that the interaction must be central, must be action and reaction. And then he obtained a force law between two current elements, which is similar to the force law of Newton, which we were discussing today. Instead of M1, M2 over R squared, it is current 1, current 2 over R squared, a central force. But this force by Ampere, which Maxwell said it should always remain the most important formula of electrodynamics, has been suppressed from all textbooks on electrodynamics, almost 99% of all textbooks on electrodynamics. And they gave the name to Ampere's circuital law, something which Ampere never wrote, that he thought against this concept. So the
Why?
physics nowadays.
Why do you think that Weber was written out of this story?
Because it just happened with
He wasn't
Faraday,
friends with the right people?
Machian, Helmholtz, people which were against Weber's approach did kick him out of history.
What didn't they like about his approach, I guess is the question.
I don't know. I think they like the other, that you need to have a mechanism of interaction, which we call nowadays field. Before that, we called ether, and so on, and so on, and so on. And with Weber, you don't have nothing of this kind. But you see, Shiloh, for this reason, I have spending the last 10, 15 years of my research translating all of these works into English, because this paradigm has been deleted, consciously deleted from the textbooks. Coulomb was never translated, with a few exceptions. Ampère was never translated, with one or two papers exception. Weber was never translated. Now, Coulomb, the whole works of Coulomb on torsion balance, electricity, magnetism have been translated into Portuguese and into English. I did publish a huge 500-page book with a colleague from USA, Buciarelli from MIT, an engineer, with Coulomb's works on torsion, electricity, and magnetism translated into English. With a colleague of mine, Shaib, we did publish Portuguese and English translations of Ampere's main book on electrodynamics, which had never been translated in 200 years. Last year, I did publish with colleagues of mine from Germany, Austria, and USA, English translations from German into English of Weber. So the title is Wilhelm Weber's Main Works on the Electrodynamics Translated into English. 4 books of 4 volumes of 500, 400, 500 pages each. After 200 years, Shiloh, these people had not been translated. This is not a coincidence. This whole paradigm was buried, was deleted from 100 years. The students didn't know about it. Let me just give an example. We were discussing here about inertia, about Mach's principle, and so on. Every kind of energy that we have is energy of interaction. For instance, the potential energy of the apple is mgh, mass of the apple, acceleration, times the distance to the earth. We have potential electrical energy, magnetic energy, elastic energy when we stretch a spring, and so on. With the exception of one kind of energy, which is kinetic energy, mv²/2. All the other energies, they are energies of interaction. With the exception of the kinetic energy, even the name, it is energy of motion, but not an energy of interaction. But if we follow the ideas of Ernst Mach, even the kinetic energy must be interaction of this body with the distant universe, and must be gravitational interaction. There is a fascinating paper by Schrödinger, 1925. I believe it was his last paper before the wave equation. This paper was published in the Annalen der Physik, the same journal where Einstein published his relativity papers and so on. this paper by Schrödinger, he begins saying, Einstein's general theory of relativity does not implement Mach's principle. But let us try to implement Mach's principle. Schrödinger was also Austrian, was influenced by the ideas of Ernst Mach. And he also wanted to implement Machian ideas. But he said, so we need to obtain the kinetic energy as an energy of interaction, like all the others. Then he said, very interesting, then he said, by this formula, mv squared over 2, I will propose heuristically, the meaning of this word heuristically is by trial and error. So I am not quoting anyone, so only my mind. By trial and error, I will propose the following potential energy. M1, M2 over R, which is the Newtonian potential energy of the apple with the earth. Parenthesis, 1 minus R dot square over C square. Why did he put R dot square? Because he wanted to deduce kinetic energy, mv squared over 2. So he said, heuristically, I will modify a little bit the Newtonian potential energy. Then he integrates always this spherical shell with a particle moving inside of it. When he integrates, the Newtonian component gives a constant. And this R dot square integrated gives a term proportional to V squared. But which is this velocity? Velocity of the body relative to the shell. And then what will be the shell? The shell will be the stars. Many shells around us. So when he integrates the energy of the apple moving relative to the stars, he obtains the kinetic energy, which is just fascinating. So it is no longer a purely kinetic energy. Now it is an energy of interaction of the apple with whom? With the stars. Which kind of interaction? Gravitational. What is the meaning of this V? Is no longer V relative to empty space. In Schrödinger, it is V relative of the apple relative to the stars. Relative velocity. So this paper is fascinating, and now this paper has already been translated into English and into Portuguese. Okay? But why I am calling attention to this fact? First, because this paper is very interesting. It is a Machian approach. The second thing, when Schrödinger published this paper, a guy called Eisner, R-E-I-S-S-N-E-R, wrote to Schrödinger and said, Schrödinger, you didn't quote me, but I had published 2 papers with this potential that you presented. And then when the collected works of Schrödinger were published, there is a letter which Schrödinger sent to Eisner and said, Eisner, I apologize. Maybe I knew your first paper, maybe not the second, because of the First World War and so on. But then he underlines the potential M1, M2 over R, parenthesis, 1 minus R dot square over C square is an intellectual property of Professor Eisner. And underline that. Okay? So that's interesting by itself. So Schrödinger acknowledged, not in his published paper, but in a private letter, that he took that idea from Eisner. But you see, both of them, they didn't know that 70 years before Eisner, this specific potential had been proposed by Weber, 1846. And both Eisner and Schrödinger were publishing in German, just like Weber, in the same journal in which Weber published most of his papers, the Annalen der Physik. But by the end of the century, Weber had disappeared from the textbooks. Schrödinger, Eisner, Einstein, none of them did know about Weber. It is amazing how things happen in physics. The history is completely deleted.
It seems to be a problem across the board in history.
I was going to ask, do you think Weber was really unlikable?
Not unlikable. He was very famous, but then the physics, not physics, science is not only facts. Physics, like everything else, is sociology, is politics, is group, is pressure, is money. So everything is involved.
Yeah.
So these questions, they are very complex, but the paradigms change. I like very much the book by Thomas Kuhn, The Structure of Scientific Revolutions. And I feel that in my skin because I fight the paradigms. Paradigms of Einstein, paradigm of Faraday, Maxwell, field theory, and so on. And so everything which Kuhn describes in this book, I feel in my skin because of the colleagues around me. When I present my works in conferences, when I try to publish papers and so on, all the reactions that you receive and how people, they simply don't know about history.
That's absolutely true.
Yeah, that is the tragic part, that you don't really have a lot of time. I think that crops up a lot in our discussions, is that when these students are coming up through the academy, there's not really any time to go back and examine the underlying
No. And people,
ideas.
they just say, no, you shouldn't go back to history. That is your waste of time, essentially, they say. And people who deal with history of physics, philosophy of physics, or teaching of physics are those which are not good students, who doesn't know real physics. The real physics must be string theory, relativity, quantum theory, and so on, and so on, and so on. But
yeah, I think that people are just not motivated to dedicate time to it unless they realize there's a problem with the knowledge that they're being handed, right?
Yes.
And so it often doesn't. It's not apparent that there's problems with that knowledge until you're pretty deep into your career, perhaps.
Yes, and for this reason, Sharon and Anastasia, is that I like what you do, because you invited people from all fields of science and even people who are outside of the academia, and you give them chance to present their ideas. And there will always be someone out there who will hear that, and that can make a difference. As I said, this happened even with what is standard nowadays. When Ernst Mach did publish his book, Newton was in the height of his fame. There was no problems with Newtonian mechanics, quite the opposite. But Ernst Mach came very bravely and said, this absolute space, that is a monstrosity. We need to get rid of that. And so on, and so on, and so on. And Einstein did hear him. And that gave rise to Einstein's general theory of relativity. I myself, I did hear him 100 years later. And that gave rise to relational mechanics. So Einstein at that time was an outsider. I am an outsider, but things can change.
That's the hope, yeah.
And they change nowadays even fast sometimes, very fast. But for this reason, what you do is so important, because in the official channels, it is very difficult to have this space to present different ideas which are outside of the mainstream. They are suppressed and so on.
It's really interesting that that seems to have always been the case, you know? I think we have the sense that that's maybe a modern problem, but it's interesting that you point to this kind of happening across centuries, essentially.
Yes, I think that will always happen. But for this reason, but nowadays, that's good that we have this possibility, this internet and so on, that people can learn from, not from textbooks, not from authorities, but from different sources.
Yeah, and they can argue about it, you know, like that's what's good about these platforms is people can, if someone doesn't like this idea, they can say why they don't like it, and hopefully that can lead to some sort of discussion that maybe moves it forward or smooths over any of the problems. I think that's why it's really important that people actually talk about it, you know, in the comments section, or they come to Discord, or, you know, they talk about it even with their local professors, like ask questions when things don't make sense. I think that's the real message here, is just, and that's all we're doing. Like, we're not trying to change the world or anything. We're just curious, and things don't make sense to us. And so that's why we invite people on the show, is because, you know, hey, this is a bit of a mystery to us. You know, this explanation we were given in college or high school is a bit unsatisfying. And so I do appreciate the work that you've done. I mean, you've been an incredibly hard worker across your career. And I think it's really important that we are simplifying our mechanics, right? And that we do actually make things, like, we've taken away one problem, right? By getting rid of this universal backdrop that is just some abstraction that doesn't make sense. At least we're in a body-centric universe all of a sudden. Now, we still have a lot of work to do, like we said, with respect to explaining the cause of these mysterious forces as well.
Sure.
But at least we've narrowed it down to a conversation between atoms, essentially, of some sort. We don't know what that conversation looks like materially yet, but we at least realize what the work needs to be done, what the job needs to be.
Yes, and as I said, this general conversation about Mach's principle, I think is so important, because, you see, with these simple experiments, when we analyze them deeply, from this Machian perspective, we see connections all with the whole universe, with the free fall of an apple. The whole universe is connected in here. So when we open our minds to these possibilities, then the same happens with biology, with other kinds. It is.
Yeah, I think the interconnected universe is like a really beautiful cosmology too. Like, I think just from, you know, we mentioned that perhaps one of the strong reasons why people are in love with this Big Bang, despite all of its failures, is because they have this need to believe in this something spiritual, right? There's a spiritual desire to believe. Yes. But I think that there's something spiritually beautiful about the interconnected universe as well, which really gives us a direct link to everything that's happening around us in a physical sense. We're very much physically connected to everything around us. And I think that's really beautiful. And like you said, it has huge ramifications for biology too, because, you know, you can't just think of yourself in a bubble, like you're just all alone, right?
Oh, yes.
Not you are like physically dependent on the trees to make you air. You're physically dependent on your friends and your family and your society and all of the animals and everything, right? But this seems to reflect the cosmos at large as well, if we take this Mach's principle seriously, that everything is in some sense dependent on everything else. And I think that's really beautiful, actually. I think people could get behind that from a spiritual standpoint.
Yes, and it's fascinating, because when we see all of this interconnectedness from different perspectives, from biology, from physics, and so on, then we open our minds. Then we can find the different connections that we never thought about them, and so that is great. So once more, so people who have an interest now, these works by Coulomb, Ampère, and Weber, they are 90% available in English. So now the whole world can read the original works.
Thank you for doing that.
This is why I put so much effort, because now they don't need to hear to me, but they can hear to Ampère himself, to Weber himself. and see what he did, which kind of experiment, how could he unify Coulomb, Ampère, and Faraday before Maxwell. Weber, in his lifetime, he published his collected works are in 6 volumes, each one with 500 pages. There is not a single page where he talked about the field. No electric field, no magnetic field. And he was a contemporary of Maxwell. He did correspond with Faraday. He did meet him. And so it was at the same time. And so it is very nice. Weber did obtain the wave equation before Maxwell, even working with direct interaction, Shiloh. It is just fascinating. 1857, many years before Maxwell did obtain the wave equation, Weber and Kirchhoff did obtain the wave equation, the telegraph equation, a signal propagating along a telegraph cable. It is just fascinating. Now these works, they are available in English. And so people can read, see the experiments, see the calculations, and be influenced by Weber directly, which is just great. So
that's awesome. And I mean, I think that's the first step in it moving into the textbooks, right? Is that more and more professors can become aware of that. You know, it really does matter, right? Like somebody reached out to me recently and was like, hey, do you want to contribute to our textbook, right? So it happens that people who are out there who hear these ideas, who have a chance, there is a real potential for people to change the needle going forward, the more people that are aware. So I really appreciate that you've done that, because I think it does definitely open up the conversation to other professors being able to examine these ideas and bring them back into the discussion. Because honestly, science is completely worthless if it's not a open inquiry where ideas can fight against other ideas. As long as you have lots of ideas fighting, it's a healthy science. As soon as you just have one idea, it's a very tyrannical and oppressive excuse for an art form, as far as I can tell. So the best thing we can do is have all of these sources and really just let the ideas fight for themselves and just see who's standing at the end of the day. And hopefully that will move us forward to solving some of these bigger questions, like what the heck is a force and everything like that. So thank you for coming today and sharing all of this.
Thank you once more for your invitation, your kindness, your openness. And so whenever you wish, I am here to talk with you. My pleasure.
All right.
Thank you so much.
Well, yeah, let's meet up again down the line again. This is always productive.
Yes,
it's always
sure.
wonderful. And you have such a wealth of knowledge about the history. And so I hope this isn't the last time we meet.
Okay, thank you very much.
Thank you so much, André.
All right.
Have a
Take care.
wonderful night.
Next time.
Bye, everybody.